So we'll start the next unit, Chapter 7, on exponential and log functions. With a little activity here, the investigate paper folding activity. I don't know if you've ever heard this, but if you take a piece of paper out of your binder right now and try to fold it in half, there is a sort of a myth that you can't fold this 7 times, that the 7th time is too hard to fold. In fact, if you try it with your paper, it would be kind of hard. But there's a Mythbusters video that tries this, and it's a little bit silly because they take a piece of paper that's like the size of a football field, and we can quickly go take a look at this video. So here it is. I'll just turn it on for a little bit. We'll watch just a minute or two.
Our team is finding out that folding a football field-sized piece of paper isn't exactly a breeze.
For instance, the fact that it turns into a giant windsock with the littlest bit of a breeze. There's air trapped underneath it.
But they managed to rein in the billowing parachute without any tears for an official fold 1.
Let it fall. Pull the slack. Oh, that was beautiful.
They reposition for the next crease.
We're gonna fold that direction.
It's like trying to fold the world's biggest bed sheet.
It's crumpling in weird ways. It's not folding smoothly.
But the team manages to smooth out the wrinkles and make folds 2, 3,
Hey, notice we're all getting a little closer?
4, 5,
Everybody to this side for 6.
and 6. Neat and tidy tuckings.
It's actually like an airbag.
However, with each pass, the additional layers make it harder to heave over. And at fold 7, everyone and everything is starting to puff.
A lot of air. Yeah, and it's not going down. There it is.
Yeah, push your foot.
7 is squashed out. Now, the team is about to go for 8. If they achieve this, they will bust the 7 paper fold myth.
See how everybody's very quiet? Because we're all anticipating busting this myth. We folded it 7 times. We're about to go for number 8.
Looking good. I think we're gonna do it.
The paper tries to dig in its heels, but is losing its grip.
Come on. And we did it! Yeah! 8! 8!
It sure feels satisfying to beat a paper myth to a pulp.
If you draw a line all the way down, you'll be able to intersect every layer, and that is a true 8 folds. And that busts this myth.
There's no stopping our out-of-control paper pushers now. If it's worth doing, it's worth over.
All right, so you get the point. It gets kind of crazy. They bring in a packer to keep folding it. So obviously you can fold it more than 7 times. That's not what this lesson is about. The lesson is about kind of equation this gives you. So if there is 0 folds, your piece of paper has 1 layer. If you fold it in half once, you end up with 2 layers. If you fold it again, if you take those 2 and you fold it again, you actually get 4 layers of paper. And this keeps happening. In fact, it's doubling every time you add a layer. And this is why when you try it with your own paper, you actually can't do it, because it gets so thick and so tiny it's hard to be able to fold. So there's going to be 64 layers of paper by the time you get to the 6th fold. Okay, so there's a pattern, and the pattern here is called exponential growth. It's not growing at an equal amount. It's like the more you fold, it's like multiplying how many layers of paper there are. Okay? In fact, in this case, what are we doing here each time? What happens each time we fold? We're actually multiplying by 2 each time. Okay, and this is what makes our exponential function. If you put that over here, this is the function that we're going to get. We get y equals, I'll explain the one later, but you're going to take 2, and how many times will you multiply it? Well, x is the number of folds. So if you would have 6 folds, for example, it would be 2 to the power 6, which is 64. Okay, so this is what is called an exponential function. We're looking for what is the patterns, or what do we have when this happens? Okay, there's a couple things you should notice. First of all, a can't be 0. Obviously, if you put 0 in the front of this equation, everything equals 0. This is an interesting one. It's always going to be positive. Okay, whatever we're multiplying by here is always going to be positive, and we're not going to multiply by an exponent, or sorry, a base of 1. Okay, because 1 to the power of anything is still going to be 1. Okay, that's not real important. Let's look at a couple of examples here. So here's what I would like you to do. This is this function. Now if you look at that in terms of our rule for an exponential function, what is a in this case? A would be 1, b is 10. Okay, and what I want you to do is graph this with your graphing calculator and see what it looks like. Okay, so I'm going to just pause there for a second, and then I'll do this on my calculator and we'll see what it looks like. So maybe we need a little bit of help remembering how to do this. So the first thing we're going to do is we're going to press Stat and Edit. And this is where you're going to put these numbers, okay, L1 and L2. All right, and if you remember, once you have this in a scatter plot and you want to graph this, what we're going to do is go to second y equals, and I'm going to turn that plot on. Or I can just go to y equals and go up here and make sure that's highlighted like it is now. And then to graph a scatter plot, you're going to go zoom 9. So here is our scatter plot. These are the values that are there. And what we want to do now is figure out what is that equation. Well, you already know what the equation is. It's y equals 10 to the power x. We could put that in there. So I could just go 10 to the power of x like this. All right. And now if I want to graph it, yeah, there it is. So it looks pretty accurate. Looks like it fits. The other way to do this, let's say we didn't know what the equation was. Remember that what you could do is you could press, we could figure out what the equation is. So let's go to Stat. All right, we want to go to Calc. And this time, it's not one of these equations. The one we want is the exponential regression, 0. So I would press 0. Oh, hang on. I got to back that up a little bit. Let's try that again. So go to Calc. The regression equation is 0. And I want to press L1 and L2, because that's what it was in the scatter plot. And this gives us what the equation is. A is 1, B is 10. And so now I want to put that into y equals, so I'll press y equals, and to paste, it's vars 5 equation enter. And there it is. Okay, if you didn't catch that, keep these keystrokes there, and I would like you to try the next few graphs. All right, I have 3 more, and then we'll analyze what they each mean. Okay, so I'm going to just close this. Just so we know, let's plot this. -3 was really low, and so these are really low values, and here this value was 1, and then it goes up really quickly. Okay, and so we had this equation that looks something like this. Okay, what are the x-intercepts? There are none. It does not cross the x-axis. Now, it kind of looked like it did on our graph, but if we would have found that, or if we would have looked, you would have seen it didn't cross. Take my word for it, it does not cross. The y-intercept is 1. The end behavior, okay, it's moving from quadrant 2 to quadrant 1. So I'll go quadrant 2, moving to quadrant 1. Okay, what is the domain? The domain is all the x values, -infinity to infinity, and the range is from 0 to infinity. Okay, 0 to infinity meaning if you look at the graph, the y values, the smallest we have is 0, and it goes all the way up to infinity. But since we don't have an x-axis, we don't include the 0. That's why it's a round bracket here. Okay, I have a few more graphs here. I would like you to do the same thing. Plot these, see what they look like on your graph and then draw it all out here and fill in the information. Okay, I'll give you a few minutes to try that, and then we'll come back. Okay, I tried graphing this one a little bit differently. What I did is I just put in the equation. All right, I put in the equation g of x is 2 times 5 to the power of x, and I just went straight to graphing it. So zoom, if you don't have to go zoom 6, zoom 9 is probably a better bet. Oops. Okay, the reason it's not going zoom 9 is because I didn't put anything in the scatter plot. I actually don't even have my plot on, so let's quickly change that. Let's put this plot back on, and now I'll go zoom 9. Okay, so those were the old points. Again, okay, as I said, I did this without, if you look here, I don't have anything in here. I didn't put the points in individually. I just wanted to show you what happens then. So now I can't use the plot, so I've turned the plot off, and then if I go zoom 9, it won't work. So if I go zoom 6, it doesn't really look quite right. Like, it's kind of hard to see here. Maybe what I'm going to do is I'm going to try zoom fit. Okay, zoom fit is zoom 0. And so it just kind of zooms in a little bit more where the graph is, and you can see that it's kind of, looks like it's hugging the x-axis here. If I want to try to find the x, see if there's an x-intercept, you can see if I just press trace, I end up at x is 0, y is 2. That's the y-intercept. But you'll see as I go this way, you know, x goes negative and y keeps getting smaller and smaller. It gets much smaller, and you're thinking to yourself, well, eventually it must get to 0. It must hit the x-intercept. So what I could do is I could say, well, maybe I should try doing the 0. Okay, so 2, that means now I have to do a left bound. So if you keep going left bound here, you're going to see it never goes to below 0. We never get a y value that's negative. That's because it never crosses the x-axis. And you may be thinking, well, how would I know that? How do I know this doesn't cross? Well, we're going to tell you right now that it doesn't, unless something goes different, and we'll talk about that another time. Right now, you don't need to worry about that. It does not cross this x-axis. Okay? Again, how do I find the y-intercept? You could go to second trace, which is calc here, and go to value. And if we put x is 0, it tells us what's the y-intercept. It's 2. Okay, now you guys always will have the calculator, so that's always going to be helpful. But we're going to find out that we probably don't even need the calculator sometimes to graph this. Okay, so hopefully you've already done this one. So this one, if you sketch it on your graph, it's going to look something like this. Okay. Come on, pen, work. All right, so this one kind of looks like it's backwards. Seems to be going down instead of up, and that's true. And the key is to consider what is the b value. If you notice the previous ones, the b value was bigger than 1. This time the b value is less than 1. Okay, so again, there's going to be no x-intercepts. The y-intercept, what is this point? Well, if you check it with your calculator, you're going to find out it's 1. Okay, and you know, you can always use your calculator for that, but just to make sure you understand, here's what we're doing. We're saying, what is h of 0? Well, that's 1/2 is to the power of 0. Anything to the power of 0 is 1. Okay, so that's why the y-intercept is 1. End behavior, we're still going from quadrant 2 to quadrant 1. The domain, just like all of these functions, is going to be negative infinity to infinity, and the range is still 0 to infinity. It still does not get quite to 0. Okay, and then we'll do this one, and this one looks very similar if you graph it, but there's a big difference. Okay, the x-intercept's none, the y-intercept is 8. End behavior, going from quadrant 2 to quadrant 1, domain negative infinity to infinity, and the range from 0 to infinity. Okay? So let's see if we can come up with some conclusions. What are the characteristics of the graph of exponential functions in the form y equals a times b to the power x? Well, you should have noticed something about a, and you should have noticed something about b. Okay, if you look at those 4 graphs we just did, if b was greater than 1, okay, so we had a couple of examples. We had b as being 5, we had b as being 10. If it's greater than 1, you're going to get a graph that looks like this. Okay, if b, now remember we said b can't be negative, but if b is greater than 0, all right, but less than 1. So maybe a better way to think of this is it's a decimal or a fraction. It's bigger than 0, but it's smaller than 1. So we had the example of a half, a fifth, decimal 2. Those are examples of something that's between 0 and 1. If that's the case, you're going to get a graph that looks like this. Okay? And then the other part of it was, what did A do? A changed the y-intercept, right? Okay, the y-intercept was the value of A. Whatever A is, that's going to be your y-intercept. Okay, so we've got those things summarized here. Notice for domain it says negative infinity to infinity. This is another way of writing it. I don't care which way you do it. Here this says y is bigger than 0. Yeah, we're saying from 0 to infinity. Okay, this is always going to be the same. Okay, and the curve will always be from quadrant 2 to quadrant 1 no matter what. The number of x-intercepts will always be 0. Okay, so we have these two situations like that. If you could do this homework, okay, just a couple of questions, that's your homework for this lesson. Okay.